Hey guys, so in this video I want to introduce you to the universal law of gravitation, and we're basically going to look at how gravity really works in a more detailed level. Let's check it out. Alright, so the force of gravity, we've been talking about this for a while. The force of gravity, which is also referred to as weight, okay, equals mg. That's what we've been doing the whole time. But it actually turns out that it's not just the Earth pulling down objects. In fact, this is a mutual attraction. Because of action-reaction, Newton's third law, it's a mutual attraction. So that means that when you are here and the Earth is pulling down on you, you are also pulling up on the Earth. It just turns out that because the Earth is way more massive than you are, you're going to accelerate down towards the Earth, and the Earth isn't really going to move towards you. Though technically, in theory, it would, but the mass difference is just too great, and you are actually not going to have an effect on the Earth. Okay? So Newton's universal law of gravitation states that every two objects attract each other. Every two objects attract each other. Okay, so again, just as the Earth attracts you, action reaction, you pull back on the Earth as well. Okay, the attraction force is weight, which is the same thing as mg. That was a simpler version of the weight equation, and now what we're going to learn is that the gravitational attraction is actually given by a more complicated equation, and that equation is big G m1 m2 over little r squared. Big G is called a universal gravitational constant, and it is given by 6.67 times 10 to the negative 11, and then a bunch of units. These are the units. You probably don't have to memorize that. Okay, 6.67 times 10 to the negative 11. It's called a universal constant because this G is the same everywhere. You might remember little g equals 9.8. Well, guess what? That's the acceleration due to gravity at the surface of the Earth. So it's actually a very specific number. One way to think about this is that in physics, big letters like big G are constants, and little letters like little g are variables. If you go to a different planet, that G is going to be different. But this G over here is always the same. So everywhere you go, G will be 6.67. So I have here two objects. Let's say that this is M1 and this is M2. And there's some distance from each other. First things first, the force will happen in a line or along a line between the two objects. So if this is the center of each object, and I draw a line connecting each other, the forces will be like this. Okay? Now, I can say that this force here is the two pulls on the one. So the idea is you have two objects. This one pulls on this, and then this pulls on this. They are pulling on each other. Okay? So this guy here, one is being pulled by two. So it's the force of two acting on one, and this is the force of one acting on two. They have the same magnitude, but they have different directions. So I can say that the magnitudes are the same, but obviously they have opposite directions because of action-reaction. Okay? Instead of writing F2-1 or 2-on-1 or 1-on-2, the direction doesn't really matter. So you could just generally refer to this as F1-2, which would be the force between 1 and 2. Okay? So that's G, that's R and R. Now, little r is a distance, not a radius. Little r is a distance. It's a distance between the object centers of mass, okay? So between centers of mass. So the idea is that the distance you're supposed to measure, it's the distance between the centers. So if you have a perfect sphere, that's going to be right down the middle. And this is the distance here, okay? So just to be clear, it's this distance between the center and not this distance here, okay? Not this distance, but the one between the centers. So one way that I have to think about this, to remember this, it's a little perverted, but if you look at this, it looks kind of like two boobs, right? With nipples here. And one way to remember this is that R is the distance between the nipples, instead of this distance here, which I guess would be the cleavage, right? So nipples, not cleavage. Okay, so hopefully that works for you. And you remember, so every two objects are attracted that way. We used to think of this attraction in terms of just mg. This is a more complicated version of that. And let's do some examples now. I want to do one, and then I want you guys to try the next one. So I have here the two identical solid spheres of mass 10. So let's just draw two. They're placed side by side without any space between them. So they're going to look like this. And they both have the same mass, so I'm just going to say m1 equals m2 equals m equals 10. Let's just call it m. And they both have the same diameter, d1 equals d2, so I'm just going to call this d, equals 60 centimeters or 0.6 meters. Okay? You might remember that in physics, we're never going to use diameter, we're always going to use radius. So I'm just going to say the radius is 0.3 meters. So I have this information. I want to find the attraction force. Attraction force it's an attraction due to gravitation, to gravity, and it's given by the equation that I just showed you guys. The attraction due to gravity, or the gravitational attraction, is given by this equation right here. Okay, G is 6.67 times 10 to the negative 11. The masses are 10 and 10. And little r is a distance, not a radius. And remember, it's a distance from here to here. And how do we do this? Well, the radius of this guy here is 0.3, and the radius of this guy here is 0.3. So the distance between these two, since they're touching side by side, is actually twice the radius. Okay, the distance is twice the radius, so it's going to be 0.6. I can square this, and I work this out. If you multiply everything, be very careful, put a lot of parentheses everywhere, right? Make sure you try this out so that you can get good at and confident that you are doing this correctly. I got 1.585 times 10 to the negative 8. Notice how that's a tiny number. Okay, we'll talk a little bit about that a little later. Cool. And now what you could do is, what I'd like you to do is to just pause the video and try this out real quick. It's similar, and we're going to be playing with that equation again. Okay, I'm going to jump right into it. The International Space Station, ISS, has a mass of this much, so let's write this down. M is 4.5 times 10 to the 5th, and it is at this height above the Earth. And then I give you the mass of the Earth. So this is the mass of the ISS. The mass of the Earth is 598 times 10 to the 24th, and it has a radius of roughly this much. So then the radius of the Earth, radius is big R, little r is distance, ends up being this, 6,370 kilometers. If you want to rewrite this in scientific notation, you get 6.37 times 10 to the 6 meters. And there's a height here. The International Space Station is at a height, let's just put it as an H, of 370 kilometers, or 3.7 times 10 to the 5th meters. Okay, everything in traditional standard units, and we want to find the ISS's weight. Okay, so one way you could have done this, you could have said, well, isn't weight just mg? Okay, isn't weight just mg? And actually it's not, because what we're going to see, and we'll talk about this more later, but as you move away from the Earth, this g here is going to decrease. So g is only 9.8 if you are on the surface of the Earth. And that's because as you move away, as two objects move away from each other, their distance, little r, increases. This entire thing here will decrease. Okay? So the attraction between two objects gets smaller as they get farther and farther away. In fact, if you're far enough from each other, if two planets are far enough from each other, they won't feel the attraction anymore because it'll be just too far away. Okay? So we wouldn't be able to do this because we don't know what g is. So the way to do this instead, to find the weight, is by using the FG equation instead. So that's what we're going to do. Okay? So I'm going to draw it over here. FG is g m1 m2 over distance squared. So I have g m1 m2. The sort of tricky part here is, what is the distance? Well, let me make a drawing. Remember, it's the distance is the distance between the centers of mass. So let's say this is the IIS over here. What matters is not this height here. It's not the radius here, the radius of the Earth, but instead it's a combination of both. So I can say that little r, and we'll see more of this later, little r is big R plus h, and I have to combine those two numbers. Okay? So if I were to do this, the numbers are 6.37 times 10 to the 6 plus 3.7 times 10 to the 5th, and then when you add both, you get 6.74 times 10 to the 6 meters. And that's the number that's going to go here. Okay? So when I do this, it's going to be 6.67 times 10 to the negative 11. The two masses, which are, this isn't going to fit here. Let me just go. So that's the equation, but we're going to continue here. 667 times 10 to the negative 11. The masses are, in no particular order, 4.5 times 10 to the 5th. 598 times 10 to the 24th. All of this divided by the distance between the two, the total distance here, which is those two numbers added, and that is squared. So I hope you can see how this is going to be. It's a huge mess, right? It's all these huge numbers multiplied against each other, or multiplied to each other. And if you do all of this, you get that the weight is 3.95 times 10 to the 6 newtons. Okay, the mass of this thing is 4.5 times 10 to the 5th. If you were to multiply this by 9.8, you would get roughly 4.4, let's say, times 10 to the 6, 4.4 times 10 to the 6. But instead we got 3.95, and that's because as you're far away, your gravity is different. Okay, so when we have these sort of problems with planets or satellites and whatnot, and I'm looking for the attraction of them, you're going to use this equation right here. Okay, let's keep going. Let me do this example here. And I have three objects that are fixed in place as shown. I want to find the net gravitational force. Gravitational force means Fg. I want to find the net force acting on M in terms of the given variables here, G, M, and L. So we're going to solve this not with numbers, but with variables. Okay? Here's the idea. I have three objects here. They each pull on each other. So this guy, let's call this A, B, and C. A is actually being pulled to the right by both of these objects. I can call this the force between A and B, and this is the force between A and C. C is being pulled to the left, right? Why? Because these guys they make a straight line with each other. They're all along a line. So C is being pulled this way by A, towards A, directly towards A. So I'm going to call this FA. C is the force between the two. And then C is also being pulled towards the left by B, F between B and C. Okay? So you draw a line between them and you figure out that they're both going towards the middle. They're both being pulled towards the middle. Now B sits in the middle, and I left this one last on purpose. B sits in the middle. B is being pulled to the left by F, by the mass A over here. So I can call this, this is also the force between A and B. And by the way, this is the same number, right? Just opposite directions. And B is being pulled to the left by C. And I'm going to call that the force BC, again, exactly like that. Okay? Just to give you a quick idea, you don't have to draw this, but let's say I have this many objects. This guy is going to be pulled in every single direction. Okay? And what I want to do is find the net force for object B. Okay? So let me do this over here. So the net force on B is the same thing as the sum of all forces on B. And there are two forces. There's a force between A and B, and there's a force between B and C. Now they're going opposite directions, so you have to put a sign here to indicate that this guy is to the left, and then this guy is just to the right, okay? But before I can do this, obviously I have to go calculate those two forces. What is the force between A and B? Well, a gravitational force is always going to be G mass 1 mass 2 over distance squared, okay? So between A and B, it's G. A and B tells me that it's between masses A and mass B, so mass A is 2m, mass B is m, and the distance between them, this is 0, this is 3L, so the gap between these two guys is 3L. The gap between these two over here is 2L, because it's from 3 to 5, and obviously the gap between A and C, we don't need that, but the gap between A and C is 5L, okay? So this gap here between A and B is 3L, and that's squared. Okay, so when I do this, I get 2G mass times mass is mass squared. This is squared, so I have a 9L squared. Okay, if you want to, you can we can kind of put this in the calculator, 2 over 9, and we'll see that this is 0.222 GM squared over L squared. Okay, let's leave it like this for now. Let's find the force between, and by the way, obviously, when we plug this in here, we're going to plug it in as a negative because it's going to the left. Let's now find FBC. So it's G, the masses, and the radius squared. So what are the masses? Well, B and C. B is M, C is 3M, and the distance between them is 2L. So I end up with 3GM squared over 4L squared. So it's 3 over 4, which is, if you want a decimal version, is this. Okay, and the reason I did a decimal version is because in this case, it's going to be easier to work this out. Now I can just plug in these forces here. FAB is going to be negative, so it's negative 0.222 GM squared over L squared plus positive 0.75 GM squared over L squared. I hope you see right away that this part here is the same, which means I can just combine this with this, but one of them is negative. So when you do this, again, very carefully, I get 0.53. Okay, so this is 0.53 GM squared over L squared. This is your force total on B, and that's part A. I know we don't have a lot of space, but we don't need a lot of space for B and C, or for part B. I'm going to carve out a little bit of room here. For part B, it says, suppose 2M comes loose. So they're fixed in place. I forgot to mention this. They're fixed in place, so they're going to be pulling each other, but not really moving. Let's say 2M comes loose. In which direction would it accelerate? Well, I hope you agree that it would accelerate to the right. And that's because the force that's pulling it to the right, this one, it's positive, so it's to the right, is greater than the force that's pulling it to the left. This is a 0.75, this is 0.22. Another way to look at it is that your net force came out as a positive, which means the positive force outweighs the negative force, or the force to the right outweighs the force to the left. So this is going to be to the right, and that's because the sum of all forces on B is positive, or the stronger force on B is to the right. So would this resulting acceleration be constant? Would this resulting acceleration be constant? Well, remember, F equals ma. So the acceleration depends on the mass and the force. Where is this force coming from? This force here is a combination of these two forces. So A has to do with, I can say that A is proportional to the gravitational force. But remember, the gravitational force is gm1m2r squared. And this is not going to be constant because as you release and the middle one starts moving to the right, the r between these two guys is going to be closer. The r between these two guys is going to be getting farther and farther, right? So because the r's will be changing, The forces will change as well. And if the forces change, the acceleration changes, okay? So it's constantly changing. In fact, what's going to happen is they're going to be getting faster and faster as they get closer to each other. And the acceleration itself will be growing, okay? So not only they're getting towards each other, they're getting faster and faster, and the acceleration is also getting greater and greater as the force gets greater, as the distance gets smaller, okay? So will it be constant? Not constant. Okay. The last point I have to make here, and I briefly mentioned this earlier, is notice how gravitational forces are very weak for non-planetary stuff. We did it here, and we got 1.85 times 10 to the negative 8. That's nothing. So basically the idea is that we're going to ignore these forces unless otherwise stated. What does that mean? Well, if you have a little a pulley with two objects, okay, you're not really going to start thinking that, oh, but they're pulling on each other and all that kind of stuff, right? So this doesn't mean that you're now going to look at everything a different way. For things that are sort of human-sized, the gravitational force doesn't really effectively do much or anything really. So we can just ignore it. We're going to consider gravitational force when we're dealing with planetary stuff, so huge masses, okay? That's it for this one. Let me know if you guys have any questions.